Hello all, welcome to the channel. The next type of isomerism is the configurational isomerism, and the isomers formed are called configurational isomers. These isomers, they have the same molecular formula, the same skeleton or the parent chain, but they differ in the configuration of the isomer. They differ in the configuration of the structure. It's because the spatial arrangement of atoms is different. Spatial arrangement of atoms or groups is different. This leads to the different configuration, and hence they are called configurational isomers. Now the first type of configurational isomerism is the geometrical isomerism. First type is the geometrical isomerism. And moreover, the conformational isomerism arises due to the non-convertibility at room temperature. For example, if you consider geometrical isomerism, we have carbon-carbon double bond. This carbon-carbon double bond or a cyclohexane ring are not interconvertible. The bond that is present here is a restricted bond. This is a restricted bond. Unlike carbon-carbon single bond, these two bonds are restricted bonds. That means at room temperature, they cannot be rotated. Rotation is restricted or not possible, because of which only the spatial arrangement of particles will vary, and hence they form configurational isomerism. The first category, geometrical isomerism, in the configurational isomerism arises when atoms or groups, when the atom or the group around the double bond is arranged differently, or the spatial arrangement is different. Spatial arrangement differs, then that results in the formation of geometrical isomers. For example, if we consider butene molecule, this is one type of arrangement, and the same butene with CH3 on the opposite side and H on the opposite side will result in one more molecule. Now this is called cis isomer, and this is called a trans isomer. This is because the methyl groups or the same type of groups are on the same side in the first case, and same groups are on the opposite side in the second molecule. Methyl groups are on the opposite side and hydrogens are on the opposite side. This results in the formation of a trans molecule. Now these two cis and trans isomers are not interconvertible. They are not interconvertible. This is because of the restricted double bond that is present in the center. They are not interconvertible. Cis and trans are completely two different molecules. As they are completely different, their physical and chemical properties will vary. Now how much physical properties are going to vary? That depends on the polarity of the molecule. Now as we are discussing about the polarity, we need to discuss about the dipole moment as well. The dipole moment of trans is 0, mu for trans is 0, and for cis mu is not equal to 0, because the same groups are on the same side. The electron pull will be only on one side or in the downward direction, and the other direction the electron density is low. So for cis molecules, dipole moment is not equal to 0, but for trans, the same groups are on the same side, so the pull of electrons will be equal and opposite in the direction. So dipole moment of cis molecules is not equal to 0, dipole moment of trans molecules is equal to 0. And if we look at the stability, Stability for trans molecules is greater than the cis molecule. Stability, if we consider, trans is more stable than the cis. This is because the bulky groups like CH3 groups are exactly opposite in direction, oppositely placed. Hence, bulky groups, if they are extreme at the extreme positions, the repulsions are going to be minimum. Repulsions are low, and hence the stability is going to be high. Trans molecules are more stable than the cis molecules. This is about geometrical isomerism with cis and trans isomers and their properties. EZ notation is an extension for the representation of geometrical isomers itself. We have already cis or trans isomers representation or notation, but still we need EZ notation. For example, when around the carbon-carbon double bond, when there is at least two same atoms or groups, then we can use cis or trans isomerism here. But if at all we have all the four different groups around the carbon-carbon double bond, then in such case cis or trans isomerism cannot be applied here. So instead we use E and Z notation for writing the configuration of this molecule. So E indicates N-tegagon, which is similar to our trans, and Z indicates Zusammen, which is similar to our cis. So cis is same as Z, trans is same as E. When we write the name, IUPAC name of the molecule, we put this E or Z in the parenthesis or square brackets or the brackets, and we mention the position where exactly the configuration is there, that is at the second carbon or third carbon or fourth carbon, etc. So this way we give the configuration. So for writing whether the given molecule is E or Z, we need to use CIP rules. What is CIP rules? It is con in gold prologue rules. These are called CIP rules. We assign priority to the attached groups based on their atomic number. We use their atomic number as the criteria and give the priority. Suppose the atomic number of this A is 2, B is 5, D is 10, C is 15. Then we give the priority for each carbon containing groups. Here among B and D, D atomic number is more. So this is given the first priority, B is given the second priority. Similarly, among C and A, C has the higher atomic number, so this is given the first priority, A is given the second priority. So around the double bond, if same priority groups are on the same side, then it is called cis isomer or Z isomer. So this configuration is Z because same priority groups are on the same side. So this is Z butene, or according to the name of the compound we need to write it. So EZ notation is an extended version for cis and trans geometrical isomers. When there are four different groups around the carbon-carbon double bond, we use con in gold prologue rules, where the priority is given to the atoms with higher atomic number, and if same prior groups are on the same side, then it is Z or Zusammen. If they are on the opposite side, then it is E or N-tegagon. This is the extended version for geometric isomerism, that is EZ notation. Let us look at the CIP rules in detail. So CIP rule says that the atom with more atomic number should be given the first priority or first number. Then atom with low Z should be given the low priority or the second number. And also if the two atoms are same, suppose C and C, but their mass numbers are different, that is C12 and C13, C13 is given the more priority. Similarly 1H1, 1H2, 1H2 is given the more priority compared to the 1H1 because of more atomic mass when the atomic number is same. So if the first connectivity is different, accordingly we give the priority based on the atomic number. But if the first connectivity is same, for example if you look at C double bond C with all carbons attached, then the next attached atom, if it varies, we should consider the second connected atom. So here all the first carbons are the same, so we need to look at the second connectivity. Here oxygen's atomic number is 8, nitrogen atomic number is 7. So oxygen will be the first priority, nitrogen will be the second priority. Similarly sulfur atomic number is 16, chlorine atomic number is 17. So this will be the first priority, this will be the second priority. Now we have same prior groups, 1 1 on the opposite side, 2 2 on the opposite side. So same prior groups on opposite side indicates E configuration. This way we can use CIP rules for giving a Z or E notation for geometrical isomers with 4 different groups on all the 4 sides.